Hey guys, so in this video we are going to go ahead and start looking at derivatives and interpreting them in a context or a situation. So already we have covered that derivative, when you are finding the derivative, you're finding an instantaneous rate of change, also known as the slope of a tangent line, but we have to start being able to deal with derivatives in actual real world situations. And so being able to use our units to really help us is going to be key, as well as just the language of questions and answers and such. So we're going to just kind of work our way through this handout and see how it goes. So in this problem, we're looking, or this activity, we're looking for phrases that are associated with certain unit sets. So for example, if I go through and you look at a couple of different things, so I'm going to do the easy ones first. So for example, an instantaneous rate of change of position. Well, position is usually measured in like meters or kilometers or miles. And so if you're doing a rate of change of that, it's that thing that's changing, your position that changes over time. So meters per second, miles per hour, feet per minute. And so that's also known as velocity. So I'm going to go ahead and in my table down here, fill in velocity. Okay. There are some possible units for acceleration then would be anything where if velocity is meters per second, acceleration is that the change of that over time. So it'd be like meters per second, or feet per minute. So those would all be acceptable units for acceleration. And now I see a couple of them on here that have per something else. So I'm actually going to pause on number 2 for a second, and we'll come back to that when we have more of a process of elimination down. Units for instantaneous rate of change of volume, V of T, where V is measured in gallons and T is measured in hours. So if volume is in gallons, and then I'm finding its rate of change, I'm doing gallons per hour. So that would be G. Possible units for position, well, this would just be anything where it's just like meters or miles, or so D right there. The instantaneous rate of change of velocity would be your acceleration. Why did I write it in there? Nobody knows. Possible units for velocity, well, we talked about this already a little bit. Meters per second would be a great one. And then last but not least, units for instantaneous rate of change of R of T. R is measured in gallons per hour. So R is already measured in gallons per hour. So this is already in gallons per hour. And I'm finding the rate of change of that over time. So then it would be per another hour. So that would be C, which by process of elimination leaves me with meters per second, which is good. That makes sense for acceleration. So that's just a really brief introduction into units and how they play out as far as rates of change go. And now we're going to get into a little more detail. So first and foremost, instantaneous versus average rate of change. Basically what happens is if you have an instantaneous rate of change, it's happening at a particular time or it's happening after 2 hours, this would be the rate at which something's happening, or you could say when t equals a very specific number. These would all be examples of something happening at an instant, whereas if it's usually over a time interval or between two numbers, or during a time interval, those would all be examples of an average rate of change. Okay, so let's go ahead and we'll look through 1 through 6 here. So it says over the time interval from 2 to 5, so that's going to be an average because it's going from 2 until 5. It's over a time interval. After 3 seconds have elapsed, well, that's at an instant. So you're looking exactly 3 seconds, and now you're looking, so that's an instant. At noon would be an instantaneous rate of change. During your first 5 minutes would be average. Over a 12-hour time period would be average, and when t equals 7 hours exactly, that would be an instantaneous. So watch the wording on them because they can be very similar, but they mean two very different things. This would imply like a derivative or your instantaneous rate of change. This is an average rate of change, or just how you find slope starting as early as Algebra 1. And like I said previously, units are going to be a big thing for indicating original functions, derivatives of those, rates versus just amounts of things. And so there's an example here. So it says, so for a function c of t, your independent variable, the thing that changes and determines how much c is. So if this was like a cost function, we could say that if you run a machine for 4 hours, the cost would be based on how long you run that machine for, right? And so the rate of change, so the rate at which that cost is changing is measured in its dependent variable over its independent variable. So dollars per hour, miles per hour, meters per second, right? So those are all dependent variables over independent variables. So if I'm looking at my next function, t is measured in seconds and a is measured in centimeters squared. So my derivative would be measured in, my rate would be measured in centimeters squared per second. My dependent variable per my independent variable. The W of V, well, W is measured in kilograms, so that's my dependent variable, so kilograms per my independent variable, cubic meters, which is a little bit weird for us. We don't usually see something that's a rate that's not involving time at all, but this would make sense, right? So if I have meters cubed would be some sort of volume. So I could say that the weight of something is increasing per the volume, right? So if my volume's increasing, and that's my independent variable, the weight would also be increasing, or the mass would also be increasing. So kilograms, the mass of the object would be increasing per the volume of the object. And then you run into weird ones like this where you already have rates. So like m of v, v is your independent variable and it's measured in miles per hour. M is measured in miles per gallon. So you could write out that your m prime of v, your derivative, is measured in miles per gallon per miles per hour. Or if you want to get really fancy, and we learned this when we're dealing with fractions a lot, miles per gallon miles per hour, flip and multiply, what ends up happening is your miles cancel out and you're left with hours per gallon, which is kind of fancy. This would also be perfectly acceptable. Okay, so really use those units to determine what your derivative is based off of what your original function was. And we're going to do that looking at some verbal descriptions. So in this example, V of t gives the volume of water in the tank in liters after t minutes. So V is measured in liters and t is what's measured in minutes. So if I did V of 3 equals 20, it's saying that when my t is 3, my V is equal to 20. So that means that after 3 minutes, there are 20 liters of water in the tank, and that's just using my original function. Now your derivative, automatically we should be able to write the units because we should feel comfortable doing our dependent variable per our independent variable. And then you just have to take into consideration the numbers. So v prime of 3, so it's still using t as that independent variable. So after 3 minutes, or at 3 minutes, the volume of the water in the tank is decreasing at a rate of 2 liters per minute. Now, it might be a little bit weird here because we see that we have a negative 2 going on, but then I just have a regular 2 here, and that's because we're dealing with the fact that our tank is decreasing. So if your rate is negative, that means your rate is going to be decreasing. So this takes, writing this word takes into the account the negative, and so then it's decreasing at a rate of 2 liters per minute implies that it is a negative rate, negative 2. Okay, if we wrote increasing, then that would mean positive. Let's do a couple examples. A of t gives the area of the surface of an oil slick in square kilometers after t hours. So that means that A is measured in kilometers squared and t is measured in hours. So A of 24 equals 17 means that after 24 hours, the area of the surface of the oil slick is 17 kilometers squared, or 17 square kilometers. A prime of 5 means, or equals 4 means that when, let's see, instead of plugging in 24, they plugged in 5. So when 5 hours, there we go, have elapsed, the area of the surface of the oil slick is, now careful, because this was -2, so it was decreasing. This is a +4, so that means that the rate is increasing, or that the area of the oil slick, is increasing at a rate of 4. And then to do my derivative units, you do your dependent variable per your independent variable. So square kilometers per hour. You also could write it like this, square kilometers per hour. That's an accepted notation as well. All right, let's do the next one. C of x gives the cost of dollars of digging a hole x feet deep. So x is measured in feet, and dollars is what gives you your C value. So C of 20 equals 140 means that it costs, let's see, the cost goes first, so the dollars goes first. So C of something equals, so it costs $140 to dig a hole that is blank deep, so something feet deep. So X is my 20, so it's 20 feet deep. This is a flip-flop of what we wrote previously, because in our first example and in our first problem that we did, we listed the independent variable first, but just the way they phrased this sentence, they listed the dependent variable first. So just pay attention to what cost is, right? Cost is C, so it should be in dollars, and then cost C equals 140, so that part goes first here. C prime of 20 equals 5 means that when the hole is, let's see, it would be when the hole is 20 feet deep, the cost of digging is, what do we say, increasing or decreasing here? Hopefully you say increasing because it's positive, at a rate of 5, and then you do your units. So it'll be your dependent variable, the rate of C over your independent variable. So I guess I should write $5 per feet dug. Not really sure about the present or past tense there. But it means that basically as they're digging the hole, it gets more costly to dig the hole the deeper they go down, right? So the cost of digging is increasing at a rate of $5 per foot dug. So as they get farther and farther down, it becomes more expensive to dig the hole, which makes sense. All right, in this one they say A of t gives the acceleration in centimeters per second squared after t seconds. So our function is actually already in centimeters per second squared, so watch out for that. And then t is in seconds. So A of 2 equals -6 means that after 2 seconds, the acceleration is -6 centimeters per second squared, because we're using just regular A. There's no derivative or anything like that. So regular A is measured using these units. Now, when we do the derivative, so A prime of 7 equals -3 means that after 7 seconds, the acceleration is, what we say, increasing or decreasing? We'd say decreasing here because it's negative. And then I'm just going to follow the same sentence structure as what we have up here, at a rate of 3, and then I do my dependent units over my independent units. So centimeters per second squared per second. Or again, if we want to get our notation 100% correct, you'd have 3, or we'd have centimeters per second squared per second, or centimeters per second cubed.